We want to find the amplitude of the steady state for any forced harmonic oscillator with the right-hand side that's sinusoidal. So in that case, if you remember, then what we're really going to be looking at is this forced response, which is A, the amplitude that we're curious about, times cosine of omega t plus our phase angle, phi. And in the last video, we found what A equaled. A was just 1 divided by this q minus omega squared plus I times p omega. A is a complex number. We could have rationalized the denominator. We could have simplified this complex number, but it turns out that our life is actually a little easier if we don't. So we're going to use that A, and we're going to specifically look at the polar form of that A, because if we look at the polar form of that complex number, that's immediately going to give us our amplitude, and it's going to immediately give us our phase angle. So what's that going to be like for our specific A? A we said was 1 over B, and B we said was q minus omega squared plus I times p omega. The cats are going at the green screen. So how do we find the modulus of this complex number? Well, there's a few ways of doing it. You might wonder whether the modulus works the same way as an absolute value, or we can just look at the denominator. And we get something really kind of interesting when we ask ourselves that question. Can we just take the reciprocal of the modulus of B? And the answer to that lies in the geometry of the complex plane. So remember that complex numbers in polar form look like this. Then if we graph the complex plane, again, that's going to be the real part of our complex number. This axis will denote the imaginary part of our complex number. Let's look at any number. It could be in any quadrant. Any number, a plus bi. So a plus bi can also be written in this form. So if this is the number, if we write it in polar form, let's say this is the number b e to the I theta. Well, then the question is, what is the reciprocal of this number? Because that's what we're really curious about. We're looking at the reciprocal of a complex number. Well, the reciprocal of this complex number is going to be 1 over b, e to the I theta. And remember properties of exponents. That's just 1 over b, e to the negative I theta. So the reciprocal of any complex number, the length of that, the modulus of the reciprocal, will just be the reciprocal of the modulus. And the angle is just going to be the negative angle. So if this is a positive theta, its reciprocal, well, it'll have a different length. And it'll look like 1 over b, e to the negative I theta. So yes, if we want to find the modulus of A, all we have to do is take the reciprocal of the modulus of B. And this is also going to be very useful in the next video when we're trying to find our new angle. The new angle, right? The angle of B, the angle of the complex number B, is just going to be the negative angle of the complex number A, which is kind of cool. Reciprocal just turns into a negative because of properties of exponents. But anyway, I'm getting ahead of myself going into the next video. So we know that that our amplitude is the modulus of A, and we just showed that the modulus of A will be 1 over the modulus of B. Because this is a complex number, we're looking at the reciprocal. What's the reciprocal of this complex number? Well, it's that. Okay. So, without further ado, what is the modulus of B? Well, we'll have to remember the modulus of a complex number. The modulus of a complex number is just its distance from 0. just the square root of a squared plus b squared. Real part squared plus imaginary part squared. So we're going to have the square root of the real part squared, that's q minus omega squared, plus the imaginary part squared, which is going to be p omega squared. This is the amplitude of our steady state, which doesn't look great, but let's explore this. This really kind of behaves somewhat similar to a reciprocal squared function. Because if you think of p and q as constants for a moment, and think about how does varying the forcing frequency affect our amplitude of our forced response, of our steady state, well, then really we have just 1 over the square root of a 4th degree polynomial, which is kind of behaves like a square root of a 4th degree polynomial kind of behaves like a 2nd degree polynomial. Let's visualize this. So what I've done over here is I've taken our amplitude function and I've graphed it on the omega axis and the amplitude axis. And actually, let me make it so that you can see all the labeling. No, it's not showing up because my body's covering it. Ha! Now my microphone's covering it. It's labeled as the omega axis. Now you can see what happens if there's no damping. And we explored this in the last section. If there's no damping, then the amplitude, here, let's make q equal 4. If there's no damping, then the natural frequency is 2. Remember, what are we talking about when I say the natural frequency is 2? We're looking back at this original differential equation. All right, if there's no damping, then the natural frequency is just going to be the square root of q, right? So the fact that we have something happen at 2 when omega is 2 should not be surprising. So yeah, if there's no damping, then we have resonance. The amplitude is just going to shoot off to infinity when the forcing frequency is equal to the natural frequency, which in this case is 2. And of course, varying the spring constant, specifically like the ratio of the spring constant to the mass, varying the spring constant is going to change our natural frequency. So as we vary this q, right, you can see that, okay, you know, wherever we have resonance is going to be different. Okay, so that's what q does. Q is going to essentially be some sort of horizontal translation. It's not, I don't know if it's perfectly a horizontal translation, but in the undamped case, it basically is. Now, P is the damping. And we said if the damping is really small, then it's very similar to the undamped version. And of course, right, here damping is very small, but it looks pretty similar. But it's not the same, right? It's not actually shooting to infinity anymore. But even if if the damping's small, we still get the same kind of behavior. If the damping's small, then we still get a big spike in amplitude when we're close to that natural frequency. And that is really, really important because, again, in the real world, nothing is undamped, not really. But things can have really small damping, and that still has crazy effects that we need to be aware of, right? Think of the swaying bridge that we talked about. Think of shattering of the glass. Those aren't actually undamped, right? They're just minimally damped, and so they have very big effects when we're in that near resonant situation. So very, very important to be aware of. And again, I said that Q is basically like a horizontal translation. You can see that it's not exactly a horizontal translation, right? It's not literally only moving left to right. The spike is getting affected as well. And so let's just pick one value of Q. Let's pick Q as 4, okay? For one value of Q, what do you think P is going to do? Well, P is 0. We have undamped, and it shoots off to infinity, the amplitude, when our frequencies are matching. And as our damping gets bigger, what do you think's happening? Oh, yeah. As our damping gets bigger, of course, we have less of a reaction to that. We have less of a reaction to that matching our frequencies. And that's going to be a really useful tool that we're going to talk about near the end of the section when looking at washing machines, of all things. And then, yeah, if your damping is enough, then of course, there's very, very little to no effect right here that we can see. And here, this is only a p-value of 2. This is not even a huge p-value. But you can see very clearly what that damping is going to do to our amplitude. This is looking at for context, always important to remember what we're looking at. We're not just looking at pretty curves. For context, we're looking at what's the relationship between the forcing frequency on the horizontal axis and the amplitude of our steady state. And it really depends on all three of these things. It depends on omega, which we graphed, and it depends on Q and P as well, the damping and the spring constant. So the less we're damping, the more that force frequency being close to the natural frequency is going to impact it. The more damping that we have, the less so that's going to matter. Okay, so we can kind of mask that pesky, crazy amplitude behavior by increasing the damping. Okay, so that's the main things. Again, you could graph this in 3 dimensions as well. We could graph it with the omega axis and the p axis, or the omega axis and the q axis, and get a 3-dimensional graph. It's going to essentially look like a 3-dimensional version of this right here. And you could also graph it in 4 dimensions if we lived in some place with 4 spatial dimensions. Or you could do a 3-dimensional graph that's like time, like with time as one of the variables, but it's not very useful, I think. I think this is the most useful way of visualizing it. So this is the way I'm doing it for us. But yeah, we really have 3, not variables, but 3 parameters that we're varying to see how they all affect the amplitude. How do they all interact with each other? Hard to view that in 2 dimensions, but hopefully this gives you a pretty good idea. In the next video, we will now talk similarly about, okay, we've analyzed how the amplitude is dependent on the damping coefficient. Again, P is not the damping coefficient, but it's really related to the damping coefficient, the spring constant, and the forcing frequency. How does that affect the phase angle? That's our next video.